Okay, welcome to Chem 652. This is the video lecture that replaces the lecture I would have given in person on Monday, February 8th. And what we're going to be discussing today are dienes and the effects of 2p orbitals in conjugation. This is a continuation of the discussion we've been having. Once again, if you're using the 4th edition of our book, we're talking about Chapter 12. If you're using the 5th edition, we're talking about Chapter 13. So let's talk about some things we've seen recently, chemical consequences of conjugation. So I've told you that conjugation impacts a lot of different reactions, and we've looked at a couple of examples. Hydrohalogenation of dienes, for example, is one we looked at recently. You actually saw this reaction for the first time last semester, but we revisited it very recently. And so, for example, if you have a conjugated diene like this one, and it's conjugated because you recognize double bond, single bond, double bond, or more specifically, if we think about each of these individual carbon atoms as being sp2 hybridized, then they all have an atomic 2p orbital available to them. So there's a total of 1, 2, 3, 4 carbon atoms, continuous carbon atoms with 2p orbitals. So a conjugated pi system is one in which there are 3 or more sp2 hybridized carbons, each with a 2p orbital aligned properly for communication. That's a conjugated pi system. So here we have this simple 1,3-butadiene, and we're reacting it with a hydrogen halide, could be HCl, HBr, or HI. And we notice that we do a Markov-Nikov hydrohalogenation, meaning that we're going to protonate across the less substituted carbon in order to form the more highly substituted carbocation, which, as we discussed, is actually a resonance delocalized allylic system. And there is a very important conjugated carbocation intermediate, the allylic cation. The halide can add to that cationic carbon, or, as we see in its other resonance form, check your notes, it can also add to the terminal carbon. You can get either a trans or a cis structure in that case. So this is all territory we've covered recently. I'm not going to go through it again today, other than just to mention the fact that we've talked about it recently. And likewise, halogenation of dienes is a reaction we talked about recently. This is polar halogenation. And we see what we could call a 1,2 addition product, in which the chlorines add across the first 2 carbons, 1 and 2. But we also get these 1,4 addition products, in which the chlorines add across carbons 1 and 4, for the same reason that when we go through the mechanism, we see that in fact there is an allylic cation involved. So both of these reactions could be termed, or I should say the products of both of these reactions could be termed either 1,2, here the hydrogen added to carbon 1, the X to 2, a 1,2 addition product, or a 1,4 addition product. In those cases, here again 1,2 and 1,4. So those are some recent reactions that we covered. Let's look at another reaction in which we will see the consequence of conjugation, a chemical consequence. So this is going to be a new one for us, and here we're going to talk about unusually fast SN1 and SN2 reactions for allylic and benzylic substrates. So what are allylic and benzylic substrates? They would look something like this. If we're talking about an SN2 reaction, then we'd want an allylic halide or a benzylic halide. Why is this an allylic halide? Well, here is this classic allyl pattern here. We've got the carbon-carbon double bond, an alkene, an sp3 hybridized carbon attached directly to the alkene functional group. This would be the allylic carbon, and likewise the halide that's on the allylic carbon would make this an allylic halide. Now, the halide in an SN1 or an SN2 reaction is going to be the leaving group, which is very important. So we've got to have that present. Over here, this is a benzylic system, and since it's a halide, we'll call it a benzylic halide because we have a benzene ring and an sp3 hybridized carbon attached directly to it, and the halogen is on the benzylic carbon. That's the benzylic carbon right there. the sp3 carbon attached to the benzene ring, the halogens on it, so it's a benzylic halide. Now what's the chemical consequence of reacting these allylic and benzylic halides in SN1 and SN2 reactions? We'll start first with the SN1 cases. What we want to note is that there are unusually fast SN1 reactions involving allylic and benzylic halides. So as an example of an SN1, this is from the first semester when we studied SN1 and SN2 chemistry. We'll go slowly here. Here we have a substrate. This carbon is attached to what appears to be a good leaving group. It is a primary carbon, which would give us cause for concern if this was a normal primary carbon. We would suspect that we couldn't undergo an SN1 reaction with the normal primary carbon, but it's not a normal primary carbon, it's an allylic carbon. And we can tell that again because this sp3 carbon is attached directly to the alkene function. Otherwise, it looks like an SN1 reaction because we don't have a strong nucleophile present. We only have a weak nucleophile, water, which is the solvent, and it's a polar solvent, which is exactly what we need for an SN1 reaction, where we're going to see spontaneous ionization of the leaving group to form a couple of charged species. It looks like a substitution reaction because we see the OH group, the OH coming from the water, has replaced or substituted for the bromine. So why is this so fast? Why is this reaction so fast compared to other SN1 reactions? We're going to have to look at the mechanism in order to answer that. So here we go. You remember that in an SN1 reaction, the first step of the mechanism is spontaneous ionization of the leaving group, and there's my 2-electron arrow indicating ionization of that leaving group, in order to give us a carbocation. But this carbocation is no ordinary carbocation. Again, if it were just an ordinary primary carbon, we'd be in big trouble here because primary carbocations don't form in solution. But in fact, it's a resonance delocalized allylic cation, and I can show the other resonance form. Like such. So there's my allylic cation. Charge delocalization stabilizes this carbocation. And of course, I still have my leaving group anion. Notice that the bromine now has 4 lone pairs. It started with 3 lone pairs, but when the bond ruptures in this heterolytic fashion, both electrons moving on to bromine, I now have a 4th lone pair and a negative charge and a bromide anion. So there is formation of the carbocation. This is the slow step. This is the rate determining step. Why is it so fast? Well, it's because it's an allylic pi system, an allylic cation, which is a stabilized cation compared to others. So the speed of this SN1 reaction is facilitated by the stability of this allylic cation. Well, what remains to finish the mechanism is simply to take either one of those 2 resonance forms and add water. Remember, in this polar solvent, our cation and our anion are likely to dissociate. There's lots of water around. Water is a weak nucleophile, but this is a desperate electrophile, so we're going to get reaction. Initially to form this oxonium ion, which we're so familiar with, and then another equivalent of water comes along, picks up the acidic proton, and we generate the final product. So the fast SN1 reaction involving an allylic system is clearly fast because of the resonance delocalized nature of this allylic conjugated cation. Let's look at another example. Here I have a benzylic system. My leaving group, the iodine, is at the benzylic carbon of this benzyl iodide molecule. I'm running this reaction not in water this time, but in a different polar solvent, methanol. And sure enough, you see that a methoxy group is now present in the product. Methanol must have acted as nucleophile and reacted at the benzylic carbon. Mechanistically, It's going to look like every other SN1 reaction you've seen, except that when we have spontaneous ionization of this leaving group, to form what at first glance appears to be a primary carbocation, we recognize that this is a massively delocalized cationic system. I'm moving pi electrons around 2 at a time, now in my third resonance form. And I'm still not done because I can still move those pi electrons over there to get to my fourth and final resonance form. And what you realize is that this carbocation is truly massively delocalized because of the conjugated pi system. The cation is part of that conjugated pi system. Why are all of these carbons, just like in the previous example, the allylic system, why are all of these carbons conjugated with one another? And the answer comes down to the fact that every single one of them is an sp2 hybridized carbon, just as we discussed in class recently. If they're all sp2 hybridized and they all have an atomic 2p orbital available to them, which they do, and all of those atomic 2p orbitals are sitting parallel to one another, as they would be here, then this is going to be a massively conjugated system, all of those 2p orbitals communicating with one another, which in this case means that they're delocalizing the charge. Well, all that remains is for me to allow my benzylic cation to react with methanol. That's the solvent I've utilized in this reaction. And that will attack to give me, once again, initially an oxonium ion, which would look like this. But of course there's trillions and trillions of alcohol molecules around. It is the solvent, and so one of them will come and deprotonate this oxonium ion to give me my final product. And notice in this last drawing here, I took the benzene ring and I put a little circle in there. That's actually a different way to indicate the pi electrons. We're about to study aromatic compounds. It's coming up very soon. And when we do, you'll see more of this sort of a representation of the pi electrons. We'll just have to hold off until then for further explanation. Coming back here, notice that I chose the resonance form which had the positive charge at the benzylic carbon. There were multiple resonance forms here, and only one had the positive charge at the benzylic carbon. We see the charge is also felt at these carbons inside the ring. Well, it turns out, again, you'll have to trust me on this because we haven't studied aromatics yet, but it's coming up very quickly. It turns out that there's something special about this benzene ring in which there are 3 pi bonds. It's a so-called aromatic molecule, and of these 4 resonance forms, this is the only one which shows the full sextet of pi electrons, meaning 6 pi electrons, which we're going to associate with this special aromatic pi system. And the long and the short of it is that, therefore, the reaction, the next step of the reaction is going to take place at the benzylic position right here in order that the product retains this aromatic sextet of pi electrons. Again, this is a very fast reaction. Looking back at the overall reaction again, it's a very fast SN1 reaction because it occurs at the benzylic position. So we've seen 2 separate fast SN1 reactions, and what's special about them is that they are so fast. As I've been telling you for a while, SN1 reactions generally are not as synthetically useful as, let's say, SN2s because they tend to be slower reactions, but these are a couple of exceptions. At an allylic and a benzylic position, the SN1 reaction is quite fast. Well, it turns out that SN2 reactions are also quite fast at both the allylic and benzylic positions. Let's look at the explanation for this. But before we talk about the explanation, let's look at an example reaction. Here's a benzylic bromide reacting with cyanide anion, which we know is an excellent nucleophile for an SN2 reaction. This is a concerted process. As always, the nucleophile will attack from the back of the carbon-leaving group bond to give us our product plus the bromide anion leaving group. So the question is, why is this reaction so fast? Well, one thing we know is that since it's an SN2 reaction, it is a concerted process. So here I've drawn the reactants again on an energy axis as a function of reaction progress. So here are the reactants, and over here are the products. Since it's a concerted process, we know there's only going to be one transition state. No intermediates and one transition state. So our energy profile would look something like this. This up here is the transition state, and we'll give that a double dagger symbol to indicate such. Well, that's nice. It shows that the SN2 reaction is a concerted process involving one transition state and no intermediates, no carbocation intermediates in particular, much like we just saw with the SN1 reaction. But it doesn't really explain why the reaction is so fast. When you talk about speeds of reaction, one of the things you really want to focus on is this energy right here, the difference in energy between the reactants and the transition states. Since I've labeled this energy axis E, we'll call this distance from reactant to transition state E sub A, and that's the activation energy. Sometimes if I use a G for Gibbs free energy over here, we'll say something like this is equal to delta G double dagger, the difference in Gibbs free energy between the reactants and the transition state. And activation energy is almost the same thing. But it's this distance right here, the mountain you have to climb, energetically speaking, before you can fall down to products, which governs the rates of any reaction. So if we say that this is a very fast reaction, one of two things must be happening. Either the reactants are sitting at unusually high energy, which would make this activation energy smaller. So that's one possibility. We bump up the energy of the reactants, keeping the transition state energy the same, and now the difference between reactant and transition state would get smaller. Or we do just the opposite. We leave the reactants where they are and we bring down the activation energy by bringing down the energy of the transition state. So in order to have a very fast reaction, we must either have unusually highly energetic reactants or unusually low energy transition states. Either of those would lead to a fast reaction. One of those two things must be happening here with this benzylic system, otherwise this SN2 reaction wouldn't be remarkably fast as it is. Well, if we look at the mechanism, we'll figure out that in fact what's going on is that the transition state energy is lowered when we run SN2 reactions with either allylic or benzylic substrates. And the best way to really figure out what might be going on is to draw what the transition state looks like. So in this particular case, the transition state might look something like this. The cyanide anion is coming in and it's starting to form a bond to that carbon, and the bromine is starting to depart, but at the transition state it's not fully departed. Now the bromide anion, once it's completely gone, is going to have a negative charge, but at this moment it has just a delta minus charge. The cyanide anion started with a negative charge, but it's starting to form a bond to the benzylic carbon, and so it's just got a delta negative at this point. Now I didn't show them over there, but there are two hydrogens at the benzylic position, and we can actually show them now. So this is a picture of the transition state. Now, if I just elaborate this picture a little bit more, we get to see that there's something pretty special about it. I could just continue the transition state onto product, and I guess I'll do that just to be complete, but that's not the essential part of this story. We're going to focus in on this transition state right here. And what I want to do is I want to go back and talk about the nature of this situation here, where we've got the nucleophile coming in and the leaving group departing. At the transition state, it turns out that the carbon, in this case the benzylic carbon, is in fact sp2 hybridized. If you go all the way back in your notes from the first semester, you'll see we talked about this once before. At the transition state, the carbon is sp2 hybridized. Starts out sp3, it's going to finish sp3, but at the transition state it's sp2. It's got a p orbital with equal size lobes on either side, which is simultaneously trying to grab onto the incoming nucleophile while hold on to the departing leaving group. Very interesting. Now, let me redraw this transition state just a little bit. What I'm going to do is I'm going to take this benzene ring and I'm going to turn it on its side. So right down here I'm going to redraw. I'll start actually with the benzylic carbon and the p orbital, I should say, and the two hydrogens attached to it, and the cyanide anion, which is coming in, and the bromide anion, which is beginning to form, the leaving group. And there's that p orbital simultaneously trying to hold on, or I should say grab on, to the nucleophile while hold on to the leaving group as it departs. And now that benzene ring I'm going to turn on its side as I indicated. And when I do that, the advantage of doing that is that now I can see exactly where those p orbitals are. Remember, this is a benzene ring which has got all these pi bonds. Every single carbon here is sp2 hybridized. So there's a p orbital at every single carbon. And there they are. And what you notice is that at the transition state, because the benzylic carbon is also sp2 hybridized, it has a p orbital which is fully conjugated to the rest of the pi system. And so we actually have delocalization of pi electron density at the transition state, and whenever we can delocalize electron density, it's always going to stabilize the system. So indeed, in this particular reaction, the reason it's so fast is that the transition state energy is lower than it might normally be. If I drop that transition state energy down there, now my new activation energy is much lower than it was initially. The reason it's dropped down is because the transition state is more stable than it might otherwise be in this benzylic system. Why is it more stable? Because it's conjugated. It's a conjugated transition state. It's a transition state with a conjugated pi system. So that's one of the effects of chemical conjugation. And of course, it's also going to be true with allylic pi systems. So here is an allyl chloride reacting with a methoxide. Because I'm using methoxide as nucleophile, it makes sense to use methanol as the solvent. This is an SN2 reaction. We know that the nucleophile is going to come from the back, the carbon leaving group bond, knock off the leaving group, and give me my products. This would be another example of an unusually fast SN2 reaction. Now SN2 reactions, if they're good ones, tend to be fast anyway. These are just even going to be faster still. So SN2 reactions involving either allylic or benzylic systems are very fast. That's the take-home message for this part of the story. And if I were to look at the transition state for this particular reaction, it might look something like this. The chloride anion is starting to depart. The methoxide anion is starting to come in. And there's my conjugated pi system. In this case, 3 carbon atoms in a row, all with 2 p orbitals that are in conjugation with one another. Okay. Well, we're going to move to the next part of our discussion now. If you need to take a break, this would be a good time to turn off the video. This won't take too terribly long from this point forward, but we do need to discuss a new type of reaction, and I will continue this discussion when I see you again on Wednesday in class. This is a very important discussion. This new reaction is known as the Diels-Alder reaction. It involves a conjugated diene, which is why we're discussing it now. This Diels-Alder reaction is also sometimes referred to as a Diels-Alder Cycloaddition, all the same thing. Very, very important reaction discovered by two chemists, one named Diels and one named Alder, and the discovery came in 1928. And it took 22 years, but in 1950 the Nobel Prize was awarded for this reaction. Now 1950 was about 65 or 66 years ago, so you might think this is an old reaction and not terribly useful any longer, but it turns out that even some 66 years later, this Diels-Alder Cycloaddition reaction continues to be one of the very most important reactions in all of organic chemistry. So of all the reactions you learned this year, this is one of the most important for sure. Let's begin by looking at an example Diels-Alder reaction. When you see a Diels-Alder cycloaddition, there's always going to be two things. There's going to be a diene, it's going to be a conjugated diene, and then this thing that reacts with the diene. Since it reacts with the diene and it's attracted to the diene, we call it a dienophile. So there's a diene and a dienophile in this reaction. Look at the diene. Notice the conformation I've drawn it in. This is a so-called S-cis conformation. S-cis conformation of this diene. And we'll talk a little bit more about that in just a second. Look at the dienophile. The dienophile is usually an alkene. This is just ethylene right here, or an alkyne. An alkene or an alkyne. And frequently the alkene or the alkyne is decorated with an electronegative group, or in other words, an electron withdrawing group. This term, electron withdrawing, will become more and more prevalent for us, especially as we get into aromatic chemistry. This dienophile I have right now shown is not decorated with anything. It's just regular old ethylene, and that's fine. Now, here's our arrow formalism. It turns out these two are going to react, and they're going to form a six-membered ring, and I'm just going to go ahead and draw dotted lines right where the new bonds of the six-membered ring will be. So you see 1, 2, 3, 4, 5, 6. That will be the six-membered ring. How do we get there? Well, it turns out that in this concerted reaction, pi electrons are circulating. I'm going to use those two pi electrons of my dienophile to create this new carbon-carbon bond, which will be formed in the product. When I do that, if that were the only thing I did, this carbon atom over here would be in violation of the octet rule. It's already got 4 bonds, including 2 to hydrogen, which aren't shown. If I only created a new carbon-carbon bond, I'd be in violation of the octet rule right there. So I need to move these pi electrons over here. Notice that in both of these two electron arrows, the arrows are pointing to where the new bond should form. That's very typical for a cycloaddition reaction like this one. We're showing, as always, that the arrows start with electrons, in this case pi electrons, but instead of pointing to an atom, they point to where the new bond will form. So I need to have that arrow somewhere in the middle there where that new bond will form, and this one somewhere in the middle where there'll be a new pi bond right there. Well, if those were the only two arrows, I'd still have a problem, because this carbon right here has already got 4 bonds, and when I shift those pi electrons over to make a new pi bond, it would have 5, a violation of the octet rule again. So the last arrow has to move those pi electrons over to show where this new bond would form. The result is I formed a 6-membered ring. Follow all of the electrons now. Those pi electrons are gone, just a single bond there. They were kicked over here to form a new pi bond, so I need to show that pi bond right there. This pi bond is gone. It's formed this new bond right here. This pi bond is gone. It's gone to form that new bond right there. So where are all the new bonds? I could sort of boldface them, I guess. There's a new bond there, a new bond there, and a new pi bond there. Those bold-faced bonds are all the new ones. But notice it's a six-membered ring, and that is really one of the main reasons that this is one of the most important reactions in all of organic chemistry. Six-membered rings are very special. They're located everywhere. They're prevalent in nature. We already talked last semester about the fact that the cyclohexane is an unusually strain-free cycloalkane molecule. This product is not a cyclohexane, but it's closely related. It's a cyclohexene. Six-membered rings are stable, prevalent in nature. You'll find them all over biologically significant molecules. If you study drug compounds for the pharmaceutical industry, you'll see them all over those. They're just a really, really important construction of carbon atoms, an architecture that shows up over and over again, plays such a significant role in our lives. So the Diels-Alder Cycloaddition, some things we need to note. It's a one-step reaction. Although we moved pi electrons all over the place all at once, it is still a one-step reaction. All of those new bonds that were being formed and all of those pi bonds which were being broken, that was all happening at the same time, which means it's a concerted reaction. And, as we were just discussing, it's a reaction that makes the all-important six-membered ring so prevalent in nature and so important in our lives. Now, I said a moment ago that the diene, here it is again, the same diene, a 1,3-butadiene in that S-cis conformation, which we'll talk about, can react with either an alkene or an alkyne. Here I have an alkyne. Once again, show the dotted lines where the new bonds are going to form. You're going to form a six-membered ring, 1, 2, 3, 4, 5, 6. These pi electrons are going to kick over there. These are going to kick over there. And these are going to kick over there. It's the same set of two electron arrows that I used a moment ago. The result is you get a six-membered ring. Notice the new pi bond that's going to be right there. This is a new bond. This is a new bond. And there's my new pi bond. But look, this was an alkyne. So there's still one pi bond left in this location here. It's not a new pi bond. It's one of the existing pi bonds from the alkyne. And the R's are still there. So my product looks like that. Look down here, I have a reaction energy diagram where I have energy plotted as a function of reaction progress. Here's my diene and my alkyne. Those are my reactants. There's my product that we just made a moment ago. Because this is a concerted cycloaddition, it's going to have one transition state. So the energy profile would look something like this. One transition state, no intermediates, no polar intermediates like carbocations or any of that. One transition state in which all of those pi electrons are moving about. That's pretty special. 6 pi electrons moving about. Well, I've been talking about this S-cis conformation, which is required for our butadiene, our diene molecule that we've used in these Diels-Alder reactions. Most of the time when we show butadiene, we show it like this. And what I want you to think about is this single bond right here in the middle of the molecule. It does have a little bit of pi electron character because it's a conjugated pi system. There's a p orbital there and a p orbital there, and they definitely share or talk to each other, share some electron density. That gives it a little bit of pi character, so it's not as easy to rotate this particular carbon-carbon single bond as it is with most carbon-carbon single bonds, let's say in an alkane, but it can be rotated, and when it is rotated, you generate the S-cis conformation. This is the S-trans conformation. Why cis and trans? Well, we're talking about S, which means single bond. It's whether it's cis or trans with respect to this single bond. You can see we've got one alkene pointing in this direction on this side of the single bond here. If I drew a line through that single bond, the alkene is on one side of the single bond and this alkene is on the other side, so this is S-trans. Over here, you can see that the alkenes are both on the same side of that single bond. This is the S-cis conformation. This cis and trans nomenclature is different than what we've normally utilized. Normally, cis and trans refers to alkenes and the substituents on the alkenes, but here it's referring to the single bond and hence the S in front of the S cis and S trans. Now, what you need to know is that the S trans conformation is not reactive in a Diels-Alder cycloaddition. If you try to bring something like this diene next to a dienophile like ethylene, it just doesn't work because you're trying to form a six-membered ring and these two carbon atoms are just too far away from those two carbon atoms. It might be close to one of them but far away from the other, and the result is you just can't simultaneously overlap that pi system in an appropriate fashion. So the S trans conformation is not reactive in a Diels-Alder cycloaddition. This reaction right here just would not occur. In order to get this to react, we need to be in an S cis conformation, and now in the S cis conformation you can see that my dienophile is close to both ends of the diene. So that's going to work. That's a Diels-Alder cycloaddition that will work for us just fine. It's interesting to note that most dienes spend their time in an S trans conformation, most of their time in an S trans conformation, and not nearly as much time in an S cis. But it is a dynamic equilibrium. Even if they spend more time in S trans, it is a dynamic equilibrium. We can rotate that carbon-carbon bond, and there is going to be S cis diene that is available for a Diels-Alder reaction, even if at equilibrium it's in the minority. Well, let's look at a couple of Diels-Alder reactions to finish things out here today. We've got this diene here. Look at this one. This diene has got these two exocyclic pi bonds. That's an interesting situation. This particular molecule cannot, in this case, adopt an S trans conformation because it's part of this ring system here. These double bonds are more or less fixed in an S cis type conformation. And that's good news for us if we're trying to do a Diels-Alder reaction because the molecule's all set up and ready to go. There are my dotted lines indicating where the new bonds are going to be. I'm going to kick these pi electrons over there, these over there, and those over there to give me a new six-membered ring. Now notice, I already had one six-membered ring. I'm going to produce a new six-membered ring right next to it. This is a fused bicyclic system that I've just created. Notice that these pi electrons kick over there. You make that new six-membered ring with the pi bond there. Because this was an alkene, not an alkyne, there's no pi bond left over here. I just have this aldehyde group. This aldehyde group could be either up or down, which means that I'm going to get a racemic mixture, an optically inactive racemic mixture, which is exactly what I should have since I started with optically inactive reactants. So that was a pretty straightforward Diels-Alder reaction. Let's look at this one down below. Here I have a diene and a dienophile, which looks a little bit different, but it's just a dienophile. This one is called maleic anhydride, and it's actually a very common dienophile, maleic anhydride. The anhydride functional group is one that we'll study a little later in the semester. It's got a carbonyl. The carbonyl carbon is attached to an oxygen, which is then attached to a second carbonyl group. That's the anhydride. This whole thing is the anhydride function, and this one's called maleic anhydride. But the problem right now is that my molecule is shown in an S trans conformation, and so I need to be aware of the fact that that can very rapidly undergo a conformational change in order to form the S cis. And as we indicated, the S trans conformation is actually going to dominate at equilibrium, but there'll still be enough of that S cis around to react with my maleic anhydride. And so once it's in the S cis conformation, which you just have to assume it will do, we can then show the Diels-Alder cycloaddition to form a new six-membered ring. And now we're attached to this 5-membered ring here. And this 5-membered ring is going to add in a syn fashion. Since it's a concerted cycloaddition, the 5-membered ring will add in a syn fashion, meaning that both of these bonds are either on the top face or the bottom face, but you won't have one top and one bottom. It's a concerted cycloaddition, so this maleic anhydride is either going to approach from the top or approach from the bottom, and it's going to add in this syn fashion here. That would be the product. Neither of these is a stereogenic center, or excuse me, they're both stereogenic centers, but the compound is a meso compound, so optically inactive, just exactly as you'd expect. And finally, our last Diels-Alder cycloaddition of the day involves another alkyne. New 6-membered ring. But because we started with an alkyne, I still have a pi bond there, and my cyano groups are still attached. So these are some Diels-Alder cycloadditions. You should be working on these now, trying to get ready for the quiz on Friday. Go to the back of the book, go to the homework, work on the Diels-Alder reactions and the other reactions as well. There might be a couple of Diels-Alder reactions in there that look a little suspicious to you. We'll talk more Wednesday about this Diels-Alder cycloaddition, and in particular we'll talk about how you can use a Diels-Alder cycloaddition to do things like this, to make not fused bicyclics but bridged bicyclics. You might remember this is a bridged bicyclic system where these carbons, which I'm putting in boldface, are called the bridge head carbons. And we'll see how we can use a Diels-Alder cycloaddition to actually produce molecules like this. So if you see homework problems that look like that, you might want to wait another day or two until we've had a chance to discuss it in class. But the other Diels-Alder homework problems you should be good to go on. I'll see you Wednesday. Take care.